Today, as we mentioned earlier, we're going to be looking at indeterminate forms, okay? Indeterminate forms. And I want to define this term first of all. We saw an example or two of this earlier in the week. But the indeterminate form is defined as the case where the limit, when we try to do direct substitution, the limit ends up giving us this 0 over 0, okay? 0 over 0. Now, why is this called an indeterminate form? Well, here's your English lesson for the day. We've got a prefix here that means not, okay? If something is innumerable, it's not able to be numbered, okay? Independent means that you are not dependent on something, okay? So we have not, and then you see here in this word determine, okay? In fact, if you remove the AT, you have the word determine, all right? But, so what this is saying is this is not able to be determined. Okay? Now that doesn't mean it's not able to be determined at all. It's just not able to be determined by direct substitution. Or you could say as easily as others. Okay? Or as other limits. Alright, so what we have to do here is we have to consider some other strategies for handling ones like these. Because you're going to run into one of two cases, okay? Anytime your denominator equaled 0, you had one of two things. What were those two things on your function? Well, it was undefined either way if your denominator equals 0. But if the denominator equals 0, you ended up, that value gave you one of two things. Do you remember? A whole or an asymptote. And as we've already seen, an asymptote, because the function will approach infinity or negative infinity, we would say the limit does not exist there. Okay? However, the process that we're actually going to look at is a process in two different methods where we can identify the wholes. Okay? So these are going to be cases where we actually are approaching a value, it's just not defined at that value. Okay? Which is what we defined earlier as a whole. So there's two strategies that we can use for this. Okay? One is dividing it out, okay? This we did back when we were looking at rational functions. We factored and divided out that factor that was causing the denominator to be 0, okay? The other strategy that we had here is rationalizing, okay? Now, when we rationalized something, what was usually involved there in that function? Or in the expression? What?
A radical.
A radical, okay? So when you see radicals in the function and you get an indeterminate form, you're going to think rationalizing, okay? So let's take a look at these two cases, all right? First of all, looking at the dividing out technique. Here we have a case where it says find the limit as x approaches 1 of x minus 1 over x cubed minus x squared plus x minus 1. Okay? So initially, you're looking at this problem and considering what we learned yesterday with our limit theorems, you say, well, great. We have a rational function. There's a polynomial on top and a polynomial on the bottom. And I know that all polynomials are continuous over all the real numbers, so I can find each of those by direct substitution. Limit as x approaches 1 of x minus 1 over the limit as x approaches 1 of x cubed minus x squared plus x minus 1. Okay? using the limit theorems we saw yesterday, I can find the limit of a rational function by doing the limit of the top over the limit of the bottom. But there was one contingency there. What was it? The denominator can't be 0. Alright? The denominator cannot be 0. So, as I plug this in, I get a 1 minus 1 over 1 minus 1 plus 1 minus 1. And I get this indeterminate form 0 over 0. So we look at that and we say, oh no, what do we do? Okay? You guys aren't awake at all, are you? Okay, come on. Alright, what do we have to do here? We have to do something else. We can't use direct substitution to find our limit. So, we're going to factor it out. Okay? Obviously the numerator doesn't factor. But the denominator, wow, that's going crazy on me. The denominator, we can factor out, alright? Here we got our 0 over 0. And the thing that we're trying to determine here when we're factoring out is we're trying to determine, is x equal 1 going to give us a whole where we will have a limit, or an asymptote? Where the limit does not exist. Okay? Now, question, how did we tell back in chapter 3, dealing with rational functions, whether that value gave us a whole or an asymptote?
Wholes cancel out, right?
Wholes come from factors that cancel out, exactly. Alright, so we've got to factor out, we've got to factor this denominator and see if we can get an x minus 1 in parentheses that will cancel out with the x minus 1 on top, because an x minus 1 is what would give us a discontinuity at 1. Alright? So, let's take a look at this, alright? First of all, factoring the denominator. We've got to factor by grouping. Okay? We've got to factor by grouping here. Remember, we can group the first two terms together, and they have a common factor of x squared. When we pull out the x squared, we have an x minus 1 left over. Okay? Notice my last two terms that I grouped together already are an x minus 1. So I'm just going to put them together in parentheses, and I understand that there's a plus 1 on the outside of those parentheses. Okay? Just bringing back to memory how we factor by grouping. Now we pull out that binomial common factor of x minus 1, and what's left over? Well, we have the x squared here and the plus 1 here. So we get x minus 1 times x squared plus 1. Okay? Everyone with me so far? Okay. So there's our factoring. Now, when I look at this in its factored form, we can see here the x minus 1 over x minus 1. And that does indeed cancel out, and look at what's left. Okay, we have a 1 over x squared plus 1. Alright, and the fact that this x minus 1 canceled out means we had a whole, and there will be a limit here. Okay? So now, once you had the whole, how did you find the actual coordinates of that whole? What, Miriam?
You plug 1 in.
Plug 1 into...
1 over x squared plus 1.
Very good. Plug in the 1. Now that you've canceled out the part that's going to make it 0 over 0, you plug that 1 in to the what's left, and we end up getting 1 over 1 squared plus 1, which is 1 over 2. Okay? And as you can see, if you were to graph this, you can see here the whole is at that point 1 1/2. Okay? So guys, we've done the mechanics or the mathematics of all of this before. Factoring it out, canceling out the common factor, and then plugging in the value to get the y coordinate of your hole. We just now have a new application of that mathematics we did before. The application is the y coordinate of that hole will now equal the limit as the function or the value of x approaches the x coordinate of the hole. Okay?
Would
Question?
you read that plus 1 for the next one?
Right here?
Yeah.
Well, we just understand, because the whole point of this is to get a common factor in the two pieces. Since this already was exactly what I was looking for here, I didn't want to factor anything out. Okay? So I understand that I can multiply 1 by anything. It's just like if you have an x, you could write that as a 1x if you want. Okay? So. Okay? Does that make sense?
Yeah.
Yes.
So the limit is the ordered pair of 1 1/2.
No, the limit is just
the 1/2.
the 1/2. Notice x is approaching 1, and the limit equals 1/2. Okay? Alright. Any questions? Other questions? Alright, good. Good. So that we've done before. We're just applying it in a new context. Let's look at another thing that we've done a little bit before we're going to apply to this context, and that is rationalizing. Okay? The rationalizing technique. Now, you'll notice here we have the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. So, as you go to evaluate this by direct substitution, because we always try that first to see if it'll work, okay? But this time we get 0 over 0. So, how did we, when we had radicals in the denominator that were part of a binomial, like for example, when we had, say, 2 over the square root of x plus 5. How did we rationalize that denominator?
X minus 5. Conjugate.
Okay, what was the
Multiply by
term?
Multiply by the conjugate.
The conjugate, okay? Because remember, if we just tried multiplying by root x over root x, will that cancel out this radical?
Yes.
Yes. But
You'll get another one.
now I'll have a radical with the 5. I just have x plus 5 root x. And that didn't help me at all. We had to multiply by the conjugate. Alright? So we have a 2 root x minus 10 over x square root of x times square root of x is just x, minus 5 root x plus 5 root x. When I'm foiling, the outers and inners will cancel out. And then minus 25. Now my denominator's rationalized. Okay? So here's the thing. We're going to use the same strategy here. Whether the radical is in the numerator or the denominator, doesn't matter. We're going to take the conjugate of that and multiply it as a form of 1. Okay? So what would the conjugate of the square root of x plus 1 minus 1 equal?
Root x plus 1 plus 1.
Root x plus 1 plus 1. Okay? So, that's what we're going to do here.
Why'd you have to rationalize every single problem?
Well, we don't have to rationalize because of, trying to get things, a radical out of the denominator or something like that in this case. we're rationalizing because in this case, rationalizing will actually make it so that when we do direct substitution, we're not going to get that 0 over 0 again. Okay? And you'll see that here in just a sec. So we had this minus 1. So now the conjugate of that is going to be square root of x plus 1 plus 1. Alright? When I'm multiplying, this is the part that's easy to mess up. Okay? So be careful with this part. When I'm multiplying these together, I have the square root of x plus 1 minus 1 times the square root of x plus 1 plus 1. Okay? So when I FOIL, I have the square root of x plus 1 squared plus 1 times square root of x plus 1 minus 1 times the square root of x plus 1 minus 1. Okay? And the whole point of doing this is that now this cancels out to 0. And look at what my numerator will end up giving me. My numerator will be this square root squared, which the square and square root cancel out. So I now have just an x plus 1 minus this one. This whole numerator just cancels down to x. Okay? Now not everyone is going to cancel out to be that simple, but you'll have those radicals. You'll have something that does not have a radical anymore. Okay? Any questions on the multiplication there? Okay, so as we do that, notice here's the simplifying. I'm going to just leave the denominator as x times square root of x plus 1 plus 1. I'm not going to distribute that in yet. Okay? But notice my numerator gets down to here. Okay? This x on the denominator what was making the denominator be 0, right? X was approaching 0, it was over x, so obviously x ended up being 0. Notice what happens again. This is where this method is similar to what we just did. This part here ends up canceling out. So x over x cancels out, and now I have just a 1 over square root of x plus 1 plus 1. Okay? So now I just proved that this expression here is the same as this expression here. So now I can take the limit of this instead as x approaches 0. Alright, and when I do that, notice I'm taking the limit of the expression I just got. I don't get 0 over 0 anymore. I end up getting 1/2. And that's where the hole in our function is. Okay, as you can see there on the graph, that's where the hole of this function is, at 0, 1/2. Okay? So notice, just like a number of our limit theorems from yesterday, we were using those theorems to get down to a point where we could actually just do direct substitution. Here, we're using this rationalizing method and the dividing out method to get to a point where we can simply use direct substitution. Okay? That's our goal here. Okay? So, any questions? Comments? Anything? Alright. Well, guess what? That's all that's new. Alright? Like I told you, the concept here isn't terribly difficult. The challenge is just putting it into practice. Okay? So, naturally, we got some practice to do. Alright? I've given you a few here with a mixture. Some of these you'll have to use dividing out. Some of these you'll have to use rationalizing. It should be pretty obvious which ones you would use which with, right? Because the rationalizing ones you're going to see radicals in, okay? Now, these ones with the trig, okay? With the trig here, you might need to use some identities, okay? Here, 27, here's one case, though, where, actually I should say here's two cases, 21 and 27, where you can use that conjugate, you can use that rationalizing idea, even though we don't see radicals, okay? There are other strategies you can use. If you happen to see something you want to try, go for it, okay? But there's a couple of strategies you can use on those. You can use the conjugate idea here on these, though, and it will work, okay? The only other thing I'll mention, notice here, what method are we going to use on number 9? Rationalizing or factoring out? T cubed minus 8 over 2 minus 2. Factoring out. What kind of factoring are we going to have to use here for our numerator? It's cubes, right? Difference of cubes. You remember how to do difference of cubes?
No.
Alright, I figured, okay? This is one of those ones that we don't use a ton, so it's easy to forget. So let's do a quick run through. I'm not going to do that one, but x cubed minus 27. Alright? Easy. It's easy to remember if you kind of just break it down into segments. It's always going to be a binomial times a trinomial. Okay? The binomial, you're just taking the cube roots of both parts. So the cube root of x cubed is x. The cube root of a negative 27 is negative 3. Okay? For the trinomial, the first term is the first term here squared. So x squared is x squared. The last term is the second one here squared. So negative 3 squared is positive 9. This last one will always be positive because you got it by squaring the whatever was here. Okay? The middle term is where you got to remember. Alright? If you take these two and multiply them together, you get negative 3x, right?
Yeah.
You put the opposite of that in the middle. Okay? So whatever this is, you put the opposite of that in the middle. Alright, so there's a little crash course on factoring difference of cubes for those you forget. Okay, I always have to think twice before I do it again, just to make sure I'm doing it right. So, easy to forget. 53 through 60, it's all calculator, okay? Graph these on your calculator, take a look at the limits. This is a good opportunity to look at these piecewise functions as you're doing the limits of piecewise functions too. Okay, those are good to be able to handle, alright? But this is calculator stuff. It's not directly what we did today, but I just wanted you to get more practice with using your calculator to find your limits with the graph. Okay? Alright, that's it. The rest of the time we're going to use to get going on the practice, okay? So, let's do that here.